Hello everybody, I'm here to talk real briefly about some of the different ways we can measure rates experimentally. Some of these methods, we always present very cleaned up data sets where everything's very idealized, and that's certainly how I'll start out. But it's good to realize, particularly if you go on to biochemistry or biology as one of your studies and you're doing kinetics as part of it, the data is often a lot more messy than this as this is in real life. And so, this is not to mislead you; it's just to teach you some of the methodologies that will be used. And so there's different ways that we can describe rates, and these are problems. You don't have to worry. You can follow along in your note sets. These are already there, worked out for you, and there's problems built in there as well. Two of the different ways are kind of on the opposite ends of the spectrum. One is the average rate of reaction, and you can look at the book. The note says has it change of moles. You could do it in terms of change in molarity. That's how I'm going to do it here. But you can think of it as over a time interval. Let's say a 10-minute interval. Looks like we have 10-minute intervals of doing a reaction going A to B. Where we're measuring the concentrations of the reactant A and the product B. We're watching A go down and we're watching A go up in this very idealized type of way. If you take the average rate over those, you can monitor the loss of A or the formation of B in this very simple scheme. And you take the change in molarity over change in T for each 10-minute interval. There's more data points than this in the note set. The big thing to notice is that the rates, which are written on the right here, are decreasing as you go down. The reason why the rates are decreasing over each one of these 10-minute intervals is because of the fact that the concentration of the reactant is dropping as you go along. And so that's rate does change over time. It's not going to be the same number in general. Now, the other way of going about that is very easy to approach algebraically. A little more challenging, I would say, is measuring the instantaneous rate of reaction. So that's the average rate of reaction, and this figures in the book. It's taking a reaction, it looks like, of butyl chloride and water forming butyl alcohol and hydrochloric acid. And what you'll see here, this in the method of instantaneous rates, that's really lends itself to calculus. What you'll see is you actually plot the concentration of a species here. We're plotting the concentration of the butyl chloride, and we're seeing that it goes down. It's not even linear. It's decreasing in a nonlinear curve type of way. It's not a straight line. Okay, so it's going down like that. And just a sketch. And so we're plotting the molarity of that versus time. The time could be in seconds, for example. And what you'll see here, the slope is a lot steeper near the beginning of the reaction than later on in the reaction, and that reflects the same type of idea we see here. The rate is decreasing over time. This is just putting it in a graphical form. And what you can do with modern data analysis, what I would do is if I want to know if the rate towards the beginning of the reaction, which is usually giving you better information because, again, in real reactions you have actually competitive chemistry going on, and there's basically perturbations or disturbances to the system that make the kinetic data harder to interpret the further you go out. But at any rate, you would basically take the tangent of a point early in the reaction. Basically, you would take a derivative of that point right on your plot near the origin, near the beginning of the reaction. The tangent method is just an old-fashioned way of doing it. You draw a tangent line off of a point near the origin of the beginning of the curve. Here it's a chemical reaction. You extrapolate it in terms of its y-axis and its x-axis, and I have an example in the notes where it's a shaded off area representing that. You can estimate it. And similarly, you can do that down here. You take a tangent of a point at a certain longer time period, 400 seconds, 500 seconds out, whatever it is, and you do a tangent curve and you extrapolate the delta, the change in terms of the concentration and the change over time, and you do a rise over run, delta concentration over delta time. That's a crude way of doing it. The way I personally would recommend is for those of you who do, when you go on next year, or if you've taken calculus already, you have your data and you work it up in a scientific program, and you do a derivative of the line that you get from your data set is the easiest way of doing it. And so that's readily doable with modern computational tools. But I just want to wrap. This is just a quick video where I just want to show two of the extreme different methods. The average rate method, where you're seeing the rate going through from time intervals. You have the bigger interval, the less information basically it has. So the here you're taking 10-minute intervals. Here you can get instantaneous rates all along the curve. But again, this lends to a little bit more arithmetic ability in terms of taking derivatives and so forth. You can estimate it with a tangent method. That's a good way to go. We're going to get into next something really powerful. I just want to make a really short video as a segue, and that's dealing with orders of reaction, how we use rate information, kinetic information to give a equation that tells us the role that all the chemical species play in terms of the mathematical form of the rate law, which will be introduced in the next video. So on that note, this was just a real short one to segue to the next video. Take care.